and child. This is my quantum gravity video 32. The topic today is revisiting and further elaboration on why the strength of gravity is only around 10 to the power minus 39 of the nuclear strong force. This is not a constant. This is not a constant. The strength of gravity is around 10 to the power minus 39. Some textbooks say it is 10 to the power minus 37, and some books say it's 10 to the power minus 40 or even 42. So this is not a constant. So it's around 10 to the power minus 39 of the nuclear strong force. And in video 13 of this series, I have explained this fact already once using two equations which can be found in page 138 of the Cambridge Handbook of Physics Formulas by author Graham Bohm, 2000 edition. And this equation is ER is equal to P cosine theta divided by 2 pi sin epsilon naught R to the power 3, where ER means electric dipole moment field. It's a force field, and it is written as P cosine theta. And PR equal to mu naught m cosine theta divided by 2 pi r to the power 3. PR here means the magnetic dipole moment field, the magnetic field dipole moment, equal to mu naught m cosine theta. What is the theta? The theta is the angle between P and R. The P is already explained is either the electric dipole moment or the magnetic dipole moment. R is the vector from the origin to the point where the force, the magnetic force or the electric force field is where it is P and R between. That means it's not exactly towards P and R, then there must be an angle theta, and that is cosine theta. How the cosine theta comes in? R is the distance from P to the charge to the charge Q. And that's not the origin. I'm sorry. It's P to the charge Q. The Q is the charge, and the length of the vector is R minus dr. I refer this to a figure here. The equation and the figure are shown here. Here's the equation. And the figure. I have to refer to this figure again later. I use these two equations to explain the huge difference in strength between the gravity and the strong force in video 13 already, because in video 13 and also previously in my video 5 of this series, I have proved that electromagnetic force and the force of gravity are actually one and the same force. And that in my video 6 of this series, I have demonstrated that the electromagnetic potential and the nuclear strong force potential of the proton are equal when the electromagnetic potential is calculated under the Coulomb's law. And the distance, or the distance means here means the Compton radius, which is equal to the Compton wavelength divided by 2 pi, as explained in my previous videos. And this is in my new hydrogen atom model. Is set at that of the proton, that is to say 0.2103 times 10 to the power minus 15 meter, thus bridging the difference in strength of electromagnetic force and the strong force. The electromagnetic force is usually said to be 1/137 of the strong force, and, but there's a difference of 1/137. That's about 100 times, a little bit more over 100 times. But when I prove that in video 6, that when the distance calculating between the charges is calculated is set as the same, that is set as 0.21073 times 10 to the power minus 15. That's the Compton radius of the proton. Then they're the same electromagnetic force and the strong nuclear force, which formerly are different by a factor of 1/137, will now become the same. That means that impliedly means the strong force actually and the electromagnetic force are one and the same force. And since I have done this proofs, so therefore I use this two equation, the electromagnetic force dipole moment and the magnetic force dipole moment, to say this two equations to show why the strength of gravity is only around 10 to the power minus 39 of the nuclear strong force. And to say that the chain of evidence is the strong force and the electromagnetic force are the same, one and the same force. And also this electromagnetic force and the gravity are the same. So I use these two equations to show why the gravity is 10 to the power minus 39 of the nuclear strong force. But maybe this is not entirely satisfactory proof, so this time I have to further elaborate this approach of mine. And I would briefly quote Richard Feynman's, the Professor Feynman's words in section 6.5 on the pages 6.6 to 6.8, inclusive of chapter 6 of the Feynman's lectures on physics, volume 2. First thing he said, we can think of an object as an assembly of point charges, Qi, that I stands for any number, so Qi means from Q1 to Q100 to Q1 billion, 1 trillion, so on. I means from 1 to infinity. In a certain region, as shown in the figure. What figure? The figure I've mentioned to you. You have the Qi here, and any one of these charges, but I've only shown 12. Of course, we know the charges must be in the number trillions in an object. And now is to find out what is the potential at the point P here due to one of the charges, and then by analogy, you will find out what is the total potential of the whole object on this single charge here at the point here. Next, Professor Feynman said, what is the potential at the point P located at R, where R is much larger than the minimum Pi? You have to refer back to the diagram again. That is to say, if the D is the distance between the origin to the Q1, the charge Qi, D is here. And if this is R, the distance from the origin to P here is much bigger than this small distance. And what happens? And Professor Feynman said the potential from the whole collection will be phi, given phi equal to 1 over 4 pi epsilon naught sigma I Qi divided by Ri, and is possibly equal to Q is over 4 pi epsilon naught R. Yeah. Ri is the distance from P to the charge Qi, and this due to the length of the vector R minus Di. Refer to the diagram again. We have Ri is this from here, Qi to P. R is from origin, R to point P. D is the the distance from origin to Qi, the charge Qi. Then this says the Ri is the length of the vector R minus Di. And Q, the big capital letter Q, is stand for the total charge of the whole object. But Professor Feynman here asked the question, what if there are two equal numbers of positive and negative charges? He said then the total charge Q of the object is 0. That if the total number of positive and negative charges are equal. He said this is not unusual. In fact, objects are usually, as we know, objects are usually neutral. And next we said, you should imagine that P is really farther away than shown in the figure. Then if ER is the E is stand for the charge E, R is the unit vector in the direction of R, then Ri is approximately equal to R minus Di ER. And then it said, since it's 1 over Ri is what we want, since Di is much smaller than R, then 1 over Ri is approximately equal to 1 over R, big capital letter R, plus bracket 1 plus Di times ER over capital letter R. And actually, all these references are to the figure. With this figure here, and this figure is taken from page 6 of the Feynman Lectures, Physics, Volume 2. And then Professor Feynman said, substituting this in phi is equal to 1 over 4 pi epsilon naught sigma Qi divided by Ri. Phi is then equal to 1 over 4 pi epsilon naught Q, capital Q, over capital R plus sigma Qi times BI times ER divided by R square plus dot 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 dot. What dot 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 means? All these terms here is just a Taylor expansion about 1 over capital R in powers of Di over R. Taylor expansion is just a mathematical method for calculating something like in sigma Qi divided by Ri. And then you said the first term, Professor Feynman said, the first term Q divided by R drops out if the object is neutral. If the object is electromagnetically neutral, then the first QR divided by R becomes 0. And the second term then becomes the important term, because the first term becomes 0. And just as for a dipole, it's 1 over r square, capital R square. And then Professor said, P, the electric dipole moment, will then be equal to sigma I Q I times di. And as a property of the charge distribution, the second term of the potential, which is the important term because the first term Q divided by R, the total charge divided by the total distance, is just 0. And then therefore the second term, which means the sigma, the summation of all the di er divided by r square, is the actual term, which is the substantial term here, substance. The second term of potential phi is equal to 1 over 4 pi epsilon naught p times e to the power r, er, not er, and divided by r square. Then this is the final result. This is the final result derived mathematically by Professor Feynman. And he says, and Feynman said, our result is here. He said, for far enough away from any mass of charges, that is, as a whole neutral. Neutral here means electromagnetically neutral. The potential is a dipole potential. The dipole potential decreases as 1 over divided by r square, and it varies as cosine theta, and its strength depends on the dipole moment of the distribution of charge. This is an important result, final result arrived by Professor Feynman. So this is how we have come back to the first equation, which I firstly mentioned. How these two equations were derived. This equation appears in the Cambridge Handbook of Physics Formula. Of course, it's just a collection of formulas by the author, but it has come from some author, some original author. The original author is of course Professor Feynman. Here. Why you see why come r square becomes r to the power 3? You have to solve some period, because here is mentioned is potential. So here become P cosine theta is a force field, is a dipole force field. So it has to become r divided by to the power 3 instead of r square. 1 over r square is for potential. 1 over r to the power 3 is for the force field. If then you have a query, why is then we instinctively think gravity is feeble, and then have no connection to these two equations. ER is equal to P cosine theta divided by 2 pi epsilon naught r free, and BR is equal to mu naught M cosine theta divided by 2 pi r to the power 3. The obvious reason, of course, is as quoted from Feynman. The both words are important words are, firstly, optics are usually neutral. When we are considering the force between electrically neutral objects, electromagnetically neutral objects, we instinctively think that only in terms of gravity, but we will never think about electromagnetic force. Another point to note from the above quote from Professor Feynman is the words far enough away from any mass of charges that is as a whole neutral. When we are considering gravity between any macroscopic objects, say between the smallest from the grains of sand to the largest, things like objects like planets and the stars and so on. The point P, as in the above figure, will definitely be far enough from the mass of charges. Even the smallest is between 2 grains of sand. This is the case, even between 2 grains of sand, because R is a macroscopic distance and dI is a microscopic distance. Macroscopic distance means you can see the naked eye. When you compare the distance between 2 grains of sand, you can see the distance with your naked eye. Whereas the dI here will be microscopic. Microscopic means you cannot see it without a microscope. And if you think of this as say this is a particle, then this distance dI here actually is microscopic, can only be seen using a scan tunneling microscope, or even can't be seen even with a scan tunneling microscope. So this R here will be, so definitely in all cases, it will be this R here in all cases will be much greater than this dI, this distance, this small distance. So this is always the case. That means this will always be, this equation will always be valid for calculating the electromagnetic force field at the point P here, due to the charges here, these charges. It's important to realize that we only mention one of the charge cubes, and actually it means that the potential of all the charges, trillions of charges, usually trillions, the collective charge at point P here. And it will always be, the total number of positive and negative charge will always be equal. If you see my video 20, I will explain that here, there. So, because the two conditions are satisfied, one is that the optics are usually neutral, electromagnetically neutral. And secondly, the distance between the objects will always much greater. They will be macroscopic, much greater than the microscopic distance between the two charges within the objects. These two conditions will always be satisfied. So this creates an illusion that gravity is extremely feeble, because I have already shown by examples in the video 13 that using these two equations, you will only always be around 10 to the power 39 of the strong force. If I briefly refer back to my video 13. They are shown in the I compare it with the proton radius, and the radius, the distance of the big distance here is r, the big r. R is the in millimeter between two grains of sand. To say, it's 10 to the power minus 3 millimeter of meter. 10 to the power minus 3 meter is millimeter, and the proton distance between protons is of the order of 10 to the power minus 15. So 0.21 times 10 to the power minus 15 bracket to the power 3 is equal to 9.26 times 10 to the power minus 48. Whereas for the millimeter, the millimeter distance, it will be the distance big R there in a figure, is 10 to the power minus 3. All to the power 3. So you equal to 2 times epsilon naught 10 to the power minus 9. So 10 to the power 9 compared with 9.26 times 10 to the power minus 48. That's just 10 to the power minus 39. This is how the small force of the gravity which we call gravity, which we deem to be gravity, because the objects are neutral. Or when the objects are neutral, then they will not consider it to be an electromagnetic force. They will consider naturally, obviously, instinctively, consider it to be gravity. But actually, it's just as mentioned in the quote from Professor Feynman, it's just the distance and the charge distribution which vary, and this variation will determine the strength of the force. And in my videos 5, firstly from video 5, and then 13 and 14 and 15 and 22 and 30 of the series, I have shown and proved that the nuclear strong force, the electromagnetic force, and the force of gravity can all be reduced to the quantum form of Planck mass divided by Planck length times c squared times an integral multiple of Planck mass. That means from one integral multiple means from 1 to infinity, 1, 2, 3, 4, 5, 6, 7 to infinity, divided by Planck length times the integral multiple number of Planck length. That also means 1, 2, 3, 4, 5, 6, 7 to infinity. This is the form. All the strong force, the electromagnetic force, and gravity can be reduced to the same form. And yeah, I have done this proof in video 5, video 13, 14, 15, 22, and 30. The distance Professor Feynman mentioned in this quote, mentioned in the quote, the worst quote is worst quoted me by above. It's a distance, firstly distance, and secondly any mass of charges or charge distribution. The distance mentioned in this video that is quoted from Professor Feynman by me, distance is exactly Planck length times c squared times integral multiple of Planck mass. I'm sorry, Planck length times integral multiple of Planck length. Integral multiple means 1 to 2, 3, 4, 5, 6, 7 to infinity. This is the distance. This distance here, r, is actually must be a multiple, an integral multiple of the Planck length. But this multiple can be extremely big, 10 to the power 30, 10 to the power 50, 10 to the power 60, and so on. And the charge, what about the charge distribution? The charge distribution is just equal to the Planck mass times c squared times integral multiple of Planck mass. Again, this integral multiple can be 1, 2, 3, 4, 5, etc. Infinity to infinity. It can be as big as 10 to the power 50, 10 to the power 60, 10 to the power 70, and so on. If you mention about the sun can be that big. As the distance and the charge distribution vary, the one and the same force, actually the strong force, the electromagnetic force, and the gravity are one and the same force. At the distance here and the charge distribution here vary. Then the strength of this force, whatever it is, we call it gravity or call it electromagnetic force or call it strong force, can be drastically varied in strength and behavior, also behavior. And this had caused the one and the same force to have been classified as nuclear strong force, the electromagnetic force, or the force of gravity, respectively. So of course, I won't say this is the only reason to why they so classified. The other reason may be because strong force is only within the proton, and whereas the electromagnetic force is usually from the proton to the surface of a hydrogen atom at 10 to the power 10 meter, 10 to the power minus 10 meter, and the force of gravity beyond to infinity distance. That may be another reason why it's so deemed to be logical to classify as three different forces, apart from the strengths of these forces. Well, so now the plan mass. What is the mass? The definition of mass. If you want to have a definition of mass, you can refer to my video 21 and video 25. And what about the charge? What's the charge distribution? If you want to have a definition of a charge, you can refer to my video 20, 21, and 27. So I will stop here for today. And if you have interested, you can subscribe and like. Bye.